So the other substitution reaction is going to be called unimolecular nucleophilic substitution, so SN1. And here once again what we're looking at is similarities and differences. So they both look like they're doing the same thing. It's just how do they go about it is going to be different, and then that's going to give them kind of different quirks. So unimolecular means there's only going to be one molecule involved in my rate determining step, and so SN1 is going to be distinctly different from SN2. But when I look at the reaction, they look very similar. So during SN1, we still have a leaving group, we still have an electrophilic carbon, we still have a nucleophile, and overall what happens is my nucleophile gets replaced with my leaving group, the leaving group leaves, the negative charge gets transferred between my nucleophile and my leaving group. And in this case, what we end up doing is kicking off a chlorine and replacing it with a hydroxide, and once we get in, we end up making an alcohol. But the one thing I want to point out is here we are doing a substitution reaction on a tertiary halogen, and what we determined last time is that you can't do an SN2 substitution reaction on a tertiary halogen, but yet we are doing a substitution reaction. So something's got to be different here. And when we say unimolecular, really what we're talking about is only one species is involved in the rate determining step. So remember with SN2, it was our electrophilic carbon and our nucleophile. Here for SN1, only our electrophilic carbon is involved in the rate determining step. The nucleophile is not involved in the rate determining step. And so that's going to have some pretty distinct changes in between how these reactions go about what you're doing. And the fact that the rate law expression is different, this implies that our mechanism is going to be different. So the mechanism of an SN2 reaction and a mechanism of our SN1 reaction are going to be a little bit different. And overall, what we're going to find is they're weirdly like mirror images of each other. So same thing if you don't see how they connect or how they interact with each other, don't worry about that. We're going to come through and summarize that all in the end. Right now, we're just saying, what about SN1 reactions? So we know, because there's only one species in the rate determining step, the mechanism is going to be a little bit different. And here, this is a lot of time when people talk about rate determining steps, this is what the example that they use in general chemistry. So SN1 reactions, the overall process is broken into two steps. So the first step is slow, and what ends up happening is we break the carbon-chlorine bond. Those electrons jump onto the chlorine, and here we end up forming this species that we'll talk about in just a second, and a negatively charged chlorine. And then the second step, that's fast, the lone pair electrons from my nucleophile attack the positively charged carbon, and we end up forming a carbon-oxygen bond. So if you think about it, overall, the same two things are happening. We form a bond between our nucleophile and our electrophilic carbon, and then we kick off our leaving group. The leaving group leaves the electrophilic carbon. In SN2, that happened in one step. In SN1, that happens in two steps, and that's kind of the big difference. And so here you can say, what do I mean by slow and fast? We mean kinetically. The first step is slow relative to the second one is fast, and we can see why. Because here, this species, the positively charged carbon, is called a carbocation, but one of the things you should notice is it has a violated octet, which means that it is relatively unstable. So in the first step, we're going from a species that has a full octet to a species that has a violated octet, which means that it's unstable, so it's hard to do. So this is kind of going uphill. We're going from stability to instability. That's hard. That's why the first step is slow. But in the second step, we are going from a species with a violated octet back to a species with a non-violated octet. So the octet rule is being followed. That's why this second step is fast, because we're going from a less stable to a more stable state. So what we need to talk about is this intermediate. So an intermediate means that it's a species that shows up inside of the mechanism, but overall it isn't part of our original reaction. So when we looked at our original reaction up here, we didn't see a carbocation, and that's because it is made and used up during our mechanism. But in this case, it's still there. It's not like a transition state. This carbocation is actually there inside of this this reaction. And so what's going to give the SN1 reaction its flavor or little quirks is the presence of this carbocation. So we need to talk about the carbocation a little tiny bit. So we kind of mentioned this before, and mainly the thing that you remember is carbocations have a violated octet, which means that they're highly reactive. So it doesn't mean you can't form a violated octet. It just means carbocations and other things with a violated octet don't want to stick around. They're going to react with something very, very quickly. So when we look at a carbocation here, we can see that it has 3 sets of electrons, and that means that overall the hybridization of the carbon inside a carbocation is sp2 hybridized. So remember, when we determine hybridization, we count electron groups. So this carbon has 1, 2, 3 electron groups. So an sp2 hybridization means that the geometry of a carbocation tends to be trigonal planar. So 3 electron groups, sp2 hybridization, trigonal planar geometry. But the one thing I want you to remember is trigonal planar geometry is flat. It's a triangle that's flat in this case, and that's going to be kind of important later on. So our carbocation is called reactive intermediate. Remember, that means that it's formed and used up in our mechanism, but it's not actually seen in the overall reaction. And the reactive intermediate is reactive. That's the idea. It's high energy, a short lifetime. We make it, and then it gets used up. And what do I mean by this? It's observed, which means that I can run tests and actually see that this carbocation is formed inside of there. And so, and the other part I want to say is these mechanisms that we give you here, they weren't pulled out of thin air. Some people have spent a lot of time doing experiments and to help provide evidence that this is actually the mechanism or how electrons move during this reaction. So this is based off of experimental data. So here, the other thing, so we look at the energy diagram of our SN1 reaction. You can see it looks a little bit different than the energy diagram of SN2. So when you look at this energy diagram, there is 2 kind of humps because we have 2 steps. And in this class, we're only going to look at, this is going to be the last energy diagram I think that we look at. Well, okay, we'll look at one more in 335B. But in energy diagrams in general, for every step in a mechanism, there is a hump. So with SN2 that we just looked at, 1 step, one hump. Here, SN1, 2 steps, 2 humps. And let's take a look at how this is going to affect our kinetics and some other things. Overall, we still are going from our reactant to our product. We're transferring a negative charge from a hydroxide to a halogen, so the products are more stable than the reactants. And so, yeah, it's going to be exothermic. But we're really not interested in that. We're interested in the rest of this stuff because that determines the kinetics. So when we look at this, the first step was slow. And the reason why was we started with some reactants that were relatively stable. Everything had a violated octet. And then we were going to our carbocation, our reactive intermediate. So we were going from something relatively stable to something relatively unstable. So that means that this jump here to go from our reactant to our transition state is relatively large. It's hard to do this because we're going to a less stable state. So we go from our reactant over our first transition state, and we'll look at what that transition state looks like here in just a second. And then we have a little valley here, so we set at the carbocation for a second. Remember, that's relatively unstable. It has a violated octet, but it's not quite as unstable as our transition states. And because this is the hard one, we're going from something stable to something unstable. The energy of activation for our first step is much larger than the energy of activation for our second step. And so we'll talk about that in just a second. That's why the first step is considered the rate determining step. The idea is if I make this first step larger or smaller, that's going to speed up my reaction. Changing what's going on with my second step does not affect anything because the larger barrier is this first step. The second barrier is kind of small. So changing the second energy of activation is not going to have an effect on my reaction. Changing the first step is going to have a lot of influence on my reaction, more importantly, the rate. So when we come back through, I'm going to summarize all this. We're going to come back through and say, what can I do to change the stability of my first transition state? So yeah, we go over the first transition state. We have a little slight dip where we go to our reactive intermediate, our carbocation, and then the carbocation relatively quickly goes to our products. So to go from something that is stable, something that's unstable to something that's stable is very easy. So the second energy of activation, the difference between my reactive intermediate and my second transition state, is relatively small. And so it's very easy to get over this. So what I want you to get from this is the thing that's determining the kinetics of my reaction is going to be this first transition state. And we will come back through and say, what can I do to stabilize or destabilize this first transition state? So yeah, and just to summarize everything I was talking about, so the first energy of activation is much larger than the second energy of activation. That's because we're in the first step, we're going from something stable to something unstable. And this is why it's called the rate determining step, because it has the larger energy of activation. And this is part of the reason why SN1 reactions are bimolecular. So the first step only involves my electrophilic carbon. Remember, the nucleophile comes in the second step. The first step is just my electrophilic carbon kicking off the halogen. So in my rate determining step, that makes it the rate determining step. So my rate law expression only involves this one species. So the nucleophile actually has very little effect on the rate of an SN1 reaction. So that's one of the big differences between SN2 and SN1. SN2 is very dependent on the nucleophile. It's involved in its rate law expression. Nucleophiles are not that important for SN1 reactions because they're not involved in the rate determining step. So when we go through, let's take a look at the two transition states. So in the first one, what's going on is we are going from a halogen and then we're going to a carbocation. So during the first step, we actually break this carbon-chlorine bond. In my transition state, we are halfway in between doing that. So this is why one bond is partial. So we are in the process of breaking this carbon-chlorine bond. And when I'm done, there's going to be a positive charge on my carbon, forming a carbocation, and then there's going to be a negative charge on my chlorine. So during this process, I'm going to have a partial positive charge on my carbon and a partial negative charge on my chlorine. So we are literally halfway into the process of forming a carbocation and negatively charged chlorine. In the second step, it's kind of the exact opposite. So remember, in the second step, we have a carbocation and my nucleophile is coming in, and my nucleophile forms a bond with my electrophilic carbon. So this oxygen-carbon bond is being showed as partial because it's in the process of being forming. When I started with, I had a full positive charge on my carbon, the carbocation, and I had a full negative charge on my nucleophile. Because we are kind of halfway in between, they both get partial. So we're in the process of losing these charges. In the product, we just have an alcohol, the carbon's neutral, the oxygen's neutral. So we are in the process of losing the positive charge on the carbon and losing the negative charge on the oxygen. So the important piece here is that carbocation. So that is inside of my transition state of the first step, we are in the process of forming a carbocation. And remember, the transition state for the first step is the important one because this is the transition state that is part of the rate determining step. So to go from the reactants to my first transition state, the energy of activation was larger. So now we need to say, what can I do to stabilize this transition state? And it has to do with the carbocation, putting a positive charge on a carbon. So we are, so if we can stabilize that carbocation, and we'll talk about that in a second, what happens is my transition state lowers in energy. And as it lowers in energy, the energy of activation decreases, and then that causes my rate of reaction to increase. So if I do something to stabilize the carbocation in an SN1 reaction, what actually happens is the reaction speeds up. As I stabilize the carbocation, the energy of activation decreases. So my transition state decreases in energy, it gets closer to the energy of the reactants. As we do that, as the energy of activation decreases, my rate increases. So it's easier to get over that energy of activation barrier, and my rate of reaction increases. So really the question is how do we stabilize a carbocation? And I'll tell you, this is kind of important. We're going to look at kind of variations of this later on, and we're going to be talking about stability, which is very important. So this idea of stability of carbocations is something that we're actually going to talk about later in this actual material. So remember about it, it's kind of important. But the idea is, how do I stabilize carbocations? And the answer to that is I add carbon substituents to them. So we're going to be going back and looking at primary, secondary, tertiary designations, but now we're looking at them in terms of a carbocation. So remember, the rules change a little bit. What are we actually looking at? With the primary, secondary, and tertiary designation, we're saying how many alkyl groups are attached to something. And for a carbocation, we're saying how many alkyl groups are actually attached directly to the carbon with the positive charge in a carbocation. For the designations, primary means there's one carbon attached to the carbon with a positive charge. That's primary. 2 carbons attached to the carbon with the carbocation, secondary. 3 carbons attached to the carbon with the carbocation, tertiary. And then remember, we still have this idea of methyl. I have literally 0 carbons attached to my carbon with a positive charge. So this is methyl, primary, secondary, and tertiary carbocations. And the idea here is, and the overall rule is, as I add alkyl groups to a carbocation, I tend to stabilize them. So between these 4 forms, the tertiary carbocation tends to be the most stable, and is definitely more stable than the methyl carbocation. And the idea is why? Why does the presence of alkyl groups adjacent to my carbocation stabilizes it? And this leads into an idea of stabilization that we haven't seen before, but stabilization is super important. We're going to find this is going to come up time and time again. We're interested in stability. One of the main questions we ask is which is more stable than something else, and we're actually going to see this applied here later on in these chapters for this exam material, where we're going to apply this specific idea that we're going to talk about right now, and that's going to help us decide what's the preferred product. So overall, the question is why are carbocations stabilized by the presence of adjacent alkyl groups? And so this process is called hyperconjugation. And what that means is, when we have a carbon as part of a carbocation, remember it is sp2 hybridized, and if you go way back, when a carbon is sp2 hybridized, it has a leftover p orbital. Normally we use that p orbital to overlap with an adjacent sp2 hybridized atom, and that would form a pi bond. I would get the overlap of adjacent p orbitals, they would form a pi bond. But in this case, with a carbocation, the p orbital is by itself, and that is where the positive charge lives. So we have 3 bonds, so I'm just showing the adjacent carbons here. In the carbocation, because the carbon is sp2 hybridized, there's a p orbital present, and that positive charge on the carbocation is present inside of that p orbital. The last thing that you need to remember is that the p orbital is kind of shaped like an infinity sign, and it tends to be along the axis, so it's like x, y, and z. So in this case, we're showing the p orbital being straight up and down. So what happens is, if I have an alkyl group that's directly adjacent to it, remember, because we have a single bond here, these CH bonds can rotate around, and in some cases they can actually become eclipsed with the p orbital. So this CH bond and this p orbital are inside of the same plane, and when this happens, the electrons from the CH sigma bond can actually donate electrons into that p orbital and stabilize the positive charge. So this is why carbocations are stabilized by having alkyl groups adjacent to it. Those the sigma bonds that are involved in alkyl groups can actually donate electron density into the p orbital, and what that does is it stabilizes the p orbital, and this process is called hyperconjugation. We're going to see this again later. Adjacent alkyl groups tend to stabilize p orbitals. So in this case, this is why tertiary carbocations are more stable than methyl or primary carbocations, is because literally there's more sigma bonds next to it. The more sigma bonds you have, the more electron density you can donate into the positive charge in the p orbital, and that tends to stabilize it. And so how does this stabilization of the carbocation affect the rates of an SN1 reaction? So here you got to remember, the easier or the more stable carbocation we can make, the easier it's going to be able to get into that transition state. So the general trends for halogens in terms of their ability to undergo SN1 reactions, it's going to be easier for a tertiary halogen. So when you kick a chlorine off of a tertiary halogen, it's going to form a tertiary carbocation. The tertiary carbocation is the most stable, and it kind of decreases. So the worst ones are like methyl and primary halogens. So remember, when I kick off the halogen or the leaving group from them, I form a primary or methyl carbocation. We don't like doing that. And the more stabilized the carbocation, the higher the SN1 rates. That's basically it, because we're trying to get to that initial transition state in between the reactants and our reactive intermediate. We're forming a carbocation. So the easier we can form the carbocation, the easier the reaction is going to be. And one of the things I want to point out is if you go back and you look at the trends for the SN2 reaction, it's the exact opposite. Remember, it was impossible to get a SN2 reaction with a tertiary halogen because of the sterics. But in this case, it's the easiest to get a SN1 reaction with a tertiary halogen because we form a carbocation. And so this gets into this crazy idea of how these two things interact. How is SN1 and SN2 related to each other? So same thing, just pointing this out. When we're done, we're going to come back through and summarize all this stuff. So just like with SN2, whenever you go through and you say, I am doing an SN1 reaction, you got to take a second and say, what are the quirks of the SN1 reaction? So every one of these reactions we're going to be talking about has these little quirks that you need to consider. And with SN2, remember, we had an inversion of stereochemistry. So if we started with R, we're going to end up with S in our product. The stereochemistry with SN1 reactions are actually lost. So no matter what I start with, so in my reactant, if I have a stereocenter and that stereocenter is, say, R, it doesn't matter. Inside of my product, what I actually do is form an equal mixture of R and S enantiomers. And remember, when we have a 50-50 mixture of R and S, that's called a racemic mixture. So stereochemistry is lost. That's what we mean. We lose stereochemical control. If I start with R, I make a mixture of R and S. Or if I start with S, what I end up making is a mixture of R and S. That's what I mean by losing stereochemical control. So why does this happen? And it comes back through to the fact that we form a carbocation intermediate. The carbocation is 3 electron groups, it's sp2 hybridized, and it's flat, it's trigonal planar. And the idea is, now our carbocation is flat, the nucleophile actually has 2 different sides that it can attack from. And depending if it attacks on one side or the other side, we end up making an R and S enantiomer, and there's really, at this point, there's nothing pushing one way or another. So it's kind of easier to see it when we think about this. When we look at the first step, so here I have a stereocenter. It started off R, and my electrophilic carbon is that stereocenter. We undergo the first step of the mechanism. What happens is we kick off the leaving group. We form our carbocation, and then my carbocation is trigonal planar. So remember, this is flat. It's kind of hard to draw, but all 3 of these bonds are inside the same plane, and my incoming nucleophile can either attack from one side or the other side. There's really no difference. And depending on which side it goes, so if it attacks on this side, the OH is going to the left, we form the S enantiomer. If it attacks to the right, the OH is going to be going to the right. We form an R enantiomer. That's what we mean by losing stereochemical control. It doesn't matter if I start with R, 100% R, or 100% S, what I'm going to be ending up making is a racemic mixture of R and S because we lose the stereocenter. So at this point, that stereocenter is gone. Remember, to have a stereocenter, I need a carbon with 4 different things attached. Well, I have a carbon with 3 different things attached to it, so there is no stereochemistry. The incoming nucleophile has a 50-50 chance of attacking one side or the other, and then what we end up doing is making 50% R or 50% S, which is a racemic